So let us look at some examples of those computationally hard problems. First example is the three-vertex color problem. The problem asks us to color the vertices of a given graph with three different colors, satisfying a certain condition, which I will explain soon. But first, let me recall one important point. Remember, we studied that any computational problem is defined so as to compute some desired output for given input. We often call an input a problem instance. In this case, the input is a graph. A graph is an object like this. It consists of vertices expressed here by small white circles and edges connecting a pair of vertices expressed here by lines. These are all examples of graphs. So they are problem instances. The input of a problem is one of these graphs. Now going back to our problem. For this problem, the input is graph. How about the output? It is a proper three coloring, a way to color the vertices of a given graph with three colors, satisfying this condition. This condition says that color those vertices so that each pair of vertices connected by an edge should have different colors. Consider this example. Suppose that this is our input graph. We want to color their vertices. Here is one coloring. Clearly, this coloring uses only three colors: blue, red, and yellow. This point is okay. But this doesn't satisfy this condition. Look at this edge. Two end vertices of this edge have the same color. So this is not a proper coloring. In other words, this is an NG coloring. On the other hand, this is a correct answer, a proper coloring. You can check each pair of endpoints of the edges is colored with a different color from one another. Well, you may take a little time to check all, but it is not so difficult. In fact, checking this condition is quite easy for computers. This is what is known as the three-vertex color problem. Let us consider another example. This is called the Hamiltonian path problem. You are once again given a graph like this, but this time the edges have directions. In this case, you need to find a way to follow the direction of the edge, a path, but do that under this condition. That is, in such a way that you go through each vertex exactly once. So the computational problem is to compute such a path for a given input graph. For example, this is one of the solutions. Number 1, number 5, number 4, number 3, 6, and 2. Taking a closer look at the graph and follow it carefully, you will see from number 1 to number 5, number 5 to number 4, number 4 to number 3, and 3 to 6, and 6 to 2 are all correspond to the directed edges of the graph. Furthermore, by this path, you went through all vertices exactly once. Again, it is not so difficult to check this condition. By the way, this problem is related to some puzzle that mathematician Hamilton proposed. So, a path satisfying this condition is called the Hamiltonian path, and the problem is called the Hamiltonian path problem. These two problems are representatives of many problems that troubled researchers. They may look like puzzles in first glance, but in fact, they are the extracted essence of the major problems that the researchers were trying to develop good algorithms with no success. So, what are the common characteristics of these problems? Here is the answer in one of the simplest forms. For a given problem instance, when a candidate solution is given, it is relatively easy to tell whether this candidate is correct or not. So this is the characteristics of this problem. Let's consider our example. In this problem, a problem instance is a given graph like this. Then the candidate solution is a coloring. That is a way to color vertices of this graph. Then, as we have seen, it is easy, at least easy for computers, to check whether candidate solutions like this to satisfy the condition of the proper coloring. So we can say that the three-vertex color problem has this property. How about the Hamiltonian path problem? Suppose this is a problem instance. Then a candidate solution is a way to traverse vertices like this. For this kind of candidate solution, the task of checking its correctness is to check whether each step of this path is consistent with the direction of the edges of the graph and all vertices are visited exactly once. Again, such a check is not so difficult. So, the Hamiltonian path problem has this property. A computational problem having this property is called an NP problem. Yes, clearly there is some reasoning for this name NP. But let me skip its explanation. In fact, I also skipped explaining what do we mean by relatively easy here. Of course, this condition is also specified precisely in the original definition. In a technical term, it is defined as the polynomial time computability, but please allow me not explaining this any further. The P for the name NP is also related to this definition, this P here. But let me skip its explanation. Note that these NP problems are not desperately hard compared with, say, incomputable problems that Turing and others discovered. We can check correctness of a candidate solution, and the number of candidate solutions is finite for each problem instance. So by trying all possible candidate solutions, we can eventually find one of the correct solutions. For example, you are asked to get a proper coloring to the graph here. And if you try all possible ways to color them like this, or like this, like this, or like this, then you will be able to find the proper coloring eventually in this way, so long as the graph has a proper coloring. That is, in principle, it is possible to compute the solution. In other words, we have an algorithm for the three-vertex color problem. In general, for any NP problem, we can at least have an algorithm for solving it like this. This is guaranteed by this property. However, there is a problem. The number of candidate solutions will become enormous. For example, in this three-vertex color problem, let us consider a graph with 60 vertices. Then each vertex would have three possible ways to color. The first vertex has three possible ways, the second one also, and third one, and so on. So by their combination, we will have 3 times 3 times 3, and so on. That is 3 to the 60s, this many possibilities, this many candidate solutions. This is an enormous number. If we were to check all these by a computer, even using the world's fastest supercomputer, it will take more than 1,000 years. That is to say, you can in principle compute the solution by this algorithm. However, it may be very inefficient and we may not be able to use it in general. This type of blow-up phenomenon can be seen basically in any NP problem, and it is called combinatorial explosion. Well, yeah, you may ask for a better algorithm, which is indeed a good question. This inefficient algorithm is one way to solve the problem, and actually, this may be a rather straightforward way. There may be a better way based on this. We may have a much better, much efficient algorithm.